now we need to consider the error. Yeah. How large is the error term? First, we need to define the error, right? Yeah. How to represent the error? So, what's the definition of the error? Definition of the error for this Tn, because we know these two expressions are different. They have different values. So the error, we take subtraction and absolute value. That's the definition of the error. And how large is the error? Yeah. So by calculation, so there is an error estimate, the upper bound. There is an upper bound for the error estimate. Capital K2, what's the meaning of capital K2? Absolute value of f double prime of x on the interval AB. Yeah. The maximum value. Yeah, you can see we need to choose the maximum value. Yeah. Upper bound. Yeah. Another way to say upper bound of the absolute value of f double prime on the given interval. So that should be a certain constant. Okay, certain constant. All right. Then the numerator, you can see the numerator is just a constant. Yeah, it's a constant number. The denominator depends on the number capital N. The larger that capital N, the smaller the error. Yeah. Now, with this inequality, you can control the precision of your approximation. Yeah. So I want to approximate the integral in a very high precision, for example, right? Yeah. So you can get it with sufficiently large number for that capital N. You can make it. Yeah, that's the idea. So that would give us confidence, right? Yeah, yeah. Because now we have powerful computers. Yeah. When we have some large number for capital N, thousands, millions, yeah, we just use computer programs to do the calculation. Yeah, yeah. In fraction of seconds. Yeah, so we can get the answer that fast. Yeah, so we have, lot of confidence here. All right. Approximate integral by area of rectangle. This time, yeah, remember the previous method we used the trapezoid pieces. This time let us use rectangle pieces. Okay, yeah. There are many different ways to approximate integral. Yeah, the areas under the curve. Yeah. All right. This time, the method we call the midpoint rule. Okay. Yeah. So the midpoint rule, we approximate the given integral using a different scheme. Okay. Different scheme. Yeah. All right. This time, we pick midterms for each small line segment piece. We select the midterm and we take the function value at this midterm, then we draw a rectangle. Rectangle. Yeah, correct. Rectangle, okay? Each piece is a rectangle. Yeah. So then we take summation of these rectangles to estimate the original integral. Yeah. Yeah. All right, yeah, another simple method. Yeah. But can you get an idea, is this method a little better or not better, comparing with the trapezoid rule? Yeah. Yeah. This midpoint rule comparing. Yeah. Yeah, depends on the shape. Yeah, but the general, yeah, depends on the shape. Yeah, it's true. Yeah, but for the general case, we say one is better. That means for high percentage. Yeah, so one method outperforms the other. Yeah, so we can still do comparison. Yeah, all right. So here, look at the property. For each rectangle, you can see some part out of upper, higher than the curve, right? Some part below the curve, some part higher than the curve, higher, below, you know, and positive, negative cancel out, make up a little bit. Yeah, from that point of view, yeah, because there is some cancellation factor we can consider. So can we treat this kind of positive, negative cancellation thing can improve the approximation, right? Yeah. So area, so because for the trapezoid method, all below the curve, right? Yeah. So it's all below the curve. Now, so we make up a little bit, okay? Yeah, some places higher, so make up the loss, right? Yeah. So here, now, let's, by accumulating the areas of all these rectangles, we have the simple formula. Yeah. All right. Yeah. So there, let's look at the error bound. Yeah. So the error, this time we use the symbol capital M sub n, yeah, as the midpoint sum. Yeah. Error of capital M n. Yeah. So the error definition. Yeah. Then the error bound. Yeah. All right. Okay. Let's see. The denominator, numerator same as before, right? Denominator 24 times n squared. Let me copy the trapezoid rule. Yeah. So you know. Yeah. Yeah. Same meaning here. Trapezoid rule T and you can see denominator slightly different. 24 versus 12. Midpoint rule, the upper bound of the error is approximately one half of the you know, the upper bound for the trapezoid rule. Okay, that means better, right? Yeah, yeah. Approximation, the you know, accuracy is better. See, accuracy is better. Yeah, one half. Yeah. All right. Yeah. So that's another simple rule we can use to calculate the integral. Yeah. Then the third rule. Yeah. This time we approximate by parabolic arcs. Yeah. So more advanced approximation by parabola. Okay, parabolic. Yeah. All right. It's called Simpson's rule. Yeah. Simpson's rule. Yeah. Yeah. All right. So now we approximate. Yeah. All right. Yeah. So here for convenience, we make n even. Yeah. Yep. Okay. Yeah. N even. Then the formula is like that. Yeah. All right. So how do we approximate, right? Yeah. So here, look at this graph. Yeah. This time we use a curve. No? Curve. The shape of the curve. So for each piece, yeah. So look, you know, for each piece, okay, the shape of the curve is a portion of parabola. Parabola. Quadratic curve. We know the equation for a parabola, right? Quadratic function. But this time we can use curve to approximate. Yeah. Not straight line. Okay? The previous two methods we use straight line. So here you can see curve-based method should fit the original function better, right? Yeah, it's a curved way to fit the original function. Yeah. All right. Error bound. Yeah. So this one we use Simpson's rule. So S, we have capital S sub n. Yeah. All right. So the error bound can be given by K4 this time. All right. That means we need to use higher derivatives, fourth derivative. Yeah. The upper bound for the fourth derivative. Yeah. All right. Yeah. So then look at the denominator. 180 times capital N to the fourth. The previous two methods, capital N squared. You can see the precision is increased. Huge. Yeah. The improvement is huge. Yeah. From N squared to N to the fourth. That much improvement. Yeah. By the Simpson's rule. Yeah. See? Yeah. So very powerful, right? Yeah. Simpson's rule. Yeah. All right. Yeah. 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 So you can see how powerful. Yeah. But you need to use some special way to, calculate the summation. Yeah. All right. Yeah. So the last one. Oh, sorry. Yeah. Last one I want to talk about. Use a specific example to look at the error estimate. Give an example. Yeah. So the function we want to approximate. Integral from 0 to 3, the function e to the negative x squared. Yeah. But here we want to use the midpoint rule. All right? Yeah. Our goal, we want to control the error, the upper bound, at the most 0.0001. And we want to see how many terms is enough. Yeah, capital N. Yeah. All right. Yeah, so let's calculate based on our error bound. So the function, we need to calculate K2, right? Second derivative. Yeah. All right. Second derivative, we can find the function of the second derivative. What is the maximum of this function on the interval from 0 to 3? Second derivative. All right? We can look at the third derivative, right? Derivative, because the typical method we use. We want to find the critical points of the second derivative, right? So we look at the third derivative, the critical points, the x values make this function 0. Yeah. All right? 0 and, so the critical point, actually, so we can see the critical point. x0 is 1. X0 is 1. Another here equals 0. X squared equals, right? Yeah. Positive, negative, because in this interval we only take positive value, right? Root of 3/2. Yeah, like that. All right. Yeah. So now let's calculate the f double prime function values at these two critical points. 0, value 2, the second critical point, that's the value. Yeah. But how large is the numerical value? 0.89. Much smaller than 2. Yeah, we should use 2. But another, because we need to calculate another value we need to look at is at endpoints, right? Other than the, internal. Yeah. So this is one of the endpoints. This is the internal critical points. But we also need to look at the value at the other endpoint, 3, right? So that's this one and much smaller. So we can make conclusion. This is the maximum. Okay? Yeah? Maximum, we can use this as our capital K2. Capital K2 is this value. Okay? Yeah? All right. Now, let's calculate error term, error part. All right? Yeah. Plug in. Yeah. Numerator, yeah. Denominator, we need to determine this capital M. Okay? Yeah, determine. Yeah. At this point, unknown. Yeah. Determine, but we want this value less than equal to our error target 0.0001. Okay? Yeah. Very small number. Yeah. Let's solve this inequality and greater or equal to 150. Yeah. So when n equals 150, yeah, we can make the error estimate part, yeah, less than or equal to this, yeah, 0.0001. Yeah, control the precision of the estimate. Yeah. All right, yeah, yeah. So now we can. This time we capital M 150. Yeah, use a program. Yeah, yeah. We get a final estimate. Yeah, this large. Okay. Yeah. All right. So that's the typical way. Yeah. So people do the approximation. Yeah. But when you do the approximation, yeah, so although we need to know the final approximation result, but you always need to do the error estimate. You need to tell people, give them your best upper bound. Okay? Yeah. So this upper bound. So yeah. 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 So you want to convince people, yeah, how accurate is your approximation. Yeah. So that is very important. Yeah. All right. Yeah. Yeah. So this is a simple example. Yeah. Yeah. So that's how much I want to do in this part D of Module 4. Yeah. Yeah. Before I finish this whole thing, so I want to ask you one question. Yeah. All right. Yeah. Because when we calculate the numerical values, yeah, so we use computer software to do the calculation. Yeah. Yeah. So the computer software, we know when we do the floating point calculation here, so we need to do the floating point calculation. Okay, all right. In computer floating point representation, because people can only use a finite many of digits after the decimal point, right? Yeah, yeah. So finite number of digits after the decimal point. Yeah. So there is a computation accuracy problem in computer-based numerical calculation. Yeah. And also here we have, this method has its own errors. Yeah. So computer has its accuracy, precision problem. Then our method has its own error problem. Yeah. So your final answer, you combine both, right? Yeah. The errors from both parts. Yeah. All right. So now there is one important question you need to think about. Yeah. So in the real world situation, yeah, for example, in the real world, so you really need to, for example, you have similar questions. Yeah. So in your final result, you produce, so you have certain integral, but you need to find the value of some special integral. Yeah. And the requirement, the technical requirement for that particular problem is you you must 100% sure the result you provided satisfy the given technical requirement, like this. Yeah. Okay? Yeah, 100%. Yeah. Yeah. So you can use more terms. Yeah. But you need to, can you, yeah, so we have some technical limitations, right? We have technical limitations. Yeah. So computer precision problem limitations. And for this method, so we may have some limitations. Okay? All right. But even with those limitations, can you find a reasonable way to guarantee your final result produced by your method is guaranteed within the given bound for the error? Yeah. So that kind of question. Yeah. Yeah. Because in the real world situation, yeah, real world situation, that is very important. Okay? Yeah. Sometimes some precision must be guaranteed. Okay? Yeah. You can use more terms. Yeah. You can do more work, more effort. But the bottom line is you cannot miss the required error bound. You cannot miss it. Okay? Yeah. Because the consequence is big. Yeah. So you don't want to take that risk. Yeah. So you would rather do more work, increase the precision. But when you do more work, how do you know you can get a good enough approximation? Now, that question. Yeah, think about that. Yeah, yeah. All right. So we finish this topic. Then we move to Module 5, so we can have a short introduction for that Fourier transform topic. Yeah. Another very important topic. Yeah. Yeah. Today we mainly do introduction part. All right. All right. Yeah. Oh, sorry. Yeah. Anyway. Yeah. So, but I need to look at the title a little bit. Fourier transform. Yeah. But we look at the Fourier cosine and the sine transforms first. Yeah. Two special cases. Yeah. Then the general case. Yeah. All right. The importance of integral transforms. Yeah. Integral. So all. Including Laplace transform, yeah. Integral transform. So let's actually, in the first half before the break time, that part, related to what we look at here. An integral transform is a transformation in the form of an integral that produces from given functions to new functions, depending on a different variable. Yeah. So here, more precisely. Yeah. So I want to, connect to what we discussed in the first half. Yeah. Depending on a different variable here. Yeah. Yeah. Because this transform, integral transform, this is a variable in a different domain. That's important. Yeah. So it's not a variable in the same domain. Okay? Yeah? Yeah, because you may have different variable, but in the same domain. Yeah. So here it's the most important part is we go to a different domain. Yeah. Yeah. All right. Yeah. Change the properties of the functions by changing the domain. Yeah. So here it talks about the domain change of functions. Yeah. Then, yeah. So when we do the change, you can see change the properties. Yeah. So how do you understand this part? Change the properties. Yeah. So my understanding. Yeah. So I may understand this phrase slightly different. Yeah. Change the properties. Yeah. So I want to understand in a way. Yeah. Because all the properties related to the given function, they are intrinsic properties of the given function. Okay? Yeah. But from the original function, we cannot discover those properties. Those properties are hidden so deep. So for ordinary people, we cannot see it. Nobody can discover it easily. Yeah. Yeah. So now we want a new method, new way to reveal those hidden properties. Okay? Yeah. Reveal those properties. All right? Yeah. So that view actually is more accurate than the change property understanding. Yeah. Change property, yeah. That means you make the change. Yeah. So the property, all right. Yeah. So you get a complete your different properties. Yeah. All right. Yeah. Although we do not say it's wrong, right? Yeah, because from the outside you see different properties. So there you feel, oh, you changed the properties. Yeah. Actually, yeah, more accurately, we reveal the hidden properties. Yeah. Because the old way you cannot see it. Yeah. The properties with different forms cannot be discovered in the old way. Okay? Now, in a new way, suddenly you can see those properties. Yeah. Yeah. So that's, I feel it's a better understanding. Yeah. So we try to expose more properties. Yeah. All right. Fourier cosine transform. Yeah. So we use cosine function. Yeah. Fourier cosine, Fourier sine. Yeah. These two basic functions. We know cosine function, sine function, they're closely related to E function, right? Yeah. By Euler formula, E function has two parts, sine, cosine, right? Yeah? So here, so let me review the Euler formula a little bit. Yeah? Yeah. Yeah. Because we use, this sine, cosine quite a lot. Yeah. E to the ix equals cosine of x plus I times sine of x. That's the Euler formula. Okay? Yeah. Yeah. And here we use both sine and cosine. Yeah. The first transform, Fourier cosine transform, we use the cosine function. Second one, Fourier sine transform, we use the sine function. Yeah. Then, because they're both related to the E function, so that you can naturally think, yeah, so probably we should use the E function. Yeah, E function. Yeah, containing both parts, cosine part and a sine part. Yeah, yeah. Pick up more information, right? Yeah, because when you use cosine function, you miss the sine components. When you use the sine function, you miss the cosine components, right? But if we use E function, we preserve both components, information from both components, right? Yeah. So that kind of understanding. All right. Yeah. But for Fourier cosine transform here, the notation. Little f sub little c, that's c cosine, okay? Yeah. Then, mathematician, they need to put a special symbol, yeah, so that, hat, yeah, veg, that kind of symbol, all right? Yeah. So that's the definition of the Fourier cosine transform. Yeah. From 0 to infinity, all right? Yeah. All right. Yeah, Fourier cosine, yeah, let's compare a little bit. Fourier cosine integral, yeah, for even function, Fourier cosine integral. Right. So we have, let's do comparisons. Yeah. Do comparisons, okay? All right. Yeah. 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 All right. Yeah. That's a function. Yeah. All right. So then, yeah. Inverse Fourier cosine transform. Inverse, yeah. Because we go to different domain, you need to come back, right? Yeah. You go to the different world, right? Different planet, for example, but eventually you need to come back, all right? To get a final job done, you need to get back to the original world, right? Yeah. So here you need the inverse Fourier cosine transform. Okay? Inverse, yeah, pretty similar, right? Yeah. So that function, you use the same kernel, right? Cosine Wx, same kernel. So you can get it back. Yeah? So that's very interesting. All right? Yeah? All right. Oh, yeah. So, yeah, let's look at a little more before we move to the next slide. All right? Yeah. The definition of cosine transform. All right. Here we call it inverse Fourier transform. Well, what do we mean here? Inverse transform. Inverse Laplace transform. Inverse transform. Right? That means, yeah, for one function, little f function, you do the transform to a different domain. Yeah. Right? Yeah. Then you do this inverse transform, you get to it, you recover the same original function. Yeah. Exactly the same function. Okay? Yeah. Yeah. All right. Yeah. And another thing, yeah. So people may get confused. Yeah, when you compare Fourier cosine transform and the Fourier cosine integral, yeah, many people may get confused. What's the difference? Yeah. From the form, it looks like, for the Fourier cosine integral, we have two formulas, right? Yeah, these two formulas. It looks like, transform, inverse transform. Similar, right? Yeah. So can we treat this as a transform? Yeah. You go to a different domain. Then we get it back. Yeah. Similar, right? Yeah. 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 So actually, yes, it's from the, calculation, the form, yeah, it's similar. It's similar. But from the formula difference, you see some small formula difference. This place, we use constant 2 over pi. This place, 1. Okay? Yeah. And here, Fourier cosine transform, root of pi, 2 over pi, root of same constant. Yeah? But that difference is not critical. Okay? Yeah, that kind of difference, not critical. Yeah. So that difference, this constant difference, because we can adjust the constant, right? Yeah? All right? Yeah. Yeah. So here, you can see, yeah, that difference is not critical. Here, actually, we use the constant 1. Yeah. We use constant 1. Yeah. Here, the constant pi. So you can see the product suppose there are two constants. Yeah. The product of these two constants is the same. The product is the same. Yeah. But why for the transform way, people like to use the same constant. Yeah. So people call it normalization. Yeah. Normalization, normalize. Yeah. Yeah. So you adjust it. So you use an appropriate constant to normalize your transform. Yeah. Yeah. So the constant is not critical. Constant just a scale, right? Yeah. You scale up, down, Yeah. Yeah. But mathematicians, they like to normalize the objects. Normalize the object. For example, people use unit vector to represent direction, right? Unit vector. Yeah. Make a unit. The length is 1. Unit vector. Okay? So that's a normalization step. If you get a vector that is not a unit vector, then you can normalize it. You divide it by its length, so you make it a unit vector. Yeah. So the process is similar like that. Yeah. Yeah. So the original. Yeah. So what non-unit? Yeah. So in math, there is a unit understanding. Yeah. Unit understanding. Yeah. So what's that unit? Yeah. There is a concept. Yeah. Some concept called a norm concept. Norm of a function. Norm equals 1. So that's a unit object. Okay? Yeah. But if the given object, its norm is not 1, you need to normalize it. Make it 1. You multiply an appropriate constant to make its norm to be 1. So that's the normalization step. Here, this constant, special root of pi over 2 over pi. So that's the normalization process. Yeah. Make its norm to be 1. Yeah. 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 So that kind of thing. All right? Yeah. So that's the, yeah. So next one, similarly, Fourier sine transform. Yeah. So we just, yeah. Right. So look at the, yeah. Similar way. Yeah. Yeah. So this time we use S, subscript S. Yeah. So we have the inverse. Yeah. All right. Yeah. All right. Yeah. But yeah. So we have a pair of transforms. Cosine version, sine version. A pair of transforms. Right. Yeah. Yeah. So other notation, yeah. Oh yeah. So then other also popular notation, because the Fourier transform, most mathematicians, they like to use the special, the curly letter. Yeah, Laplace also curly letter, right? Yeah. So the Fourier transform, yeah, people like to make it special. Yeah, because these transforms are very important. People want to make it very special. Yeah. Yeah. So using those special characters. Yeah. Inverse. Yeah. So inverse. Yeah. So yeah. Yeah. So when I type, sometimes, yeah, because so I use the fonts symbol from Microsoft PowerPoint tools. Yeah. So it's not easy to find those symbols. I just use a close one. Yeah. Yeah. So you know it. Yeah. For Laplace transform, I use, L, similar to this kind of error, L, not the, very curly error, letter. Yeah. All right. All right. Next, linearity and the transforms of derivatives. Yeah. Let's look at linearity. Yeah. So, remaining 5 minutes. Yeah. Linearity, very simple. Yeah. We just look at the linearity property. Yeah. Very simple. Yeah. Linearity, yeah. So you apply the transform on the linear combination of two functions, so you can use the, linear combination of their transforms. Yeah. So pretty straightforward. Yeah. So for these two transforms, you have those linearity property. Yeah. So derivative, so you have that. Because derivative, you can do integration by parts, right? Yeah. So these formulas, yeah. So just do the calculation in integration by parts. Yeah? So you can get that easily. Yeah. Because integration by parts, you need to use the limits, right? Yeah. When x goes to infinity, the function value also goes to infinity, because you need to evaluate the limits, the function value at two integral limits, upper, lower 0, very easy to but the upper one, you need to evaluate it at infinity, so you take limits. Yeah. With this limits, it's gone. It's 0. It's gone. So you have that. Yeah. So here it's like the proof, right? Yeah. So here I did, integration by parts. Because the limit, you take the limit, right? So when x goes to infinity, f function goes to infinity, cosine is a bounded function, right? A bounded function times, limit is 0. Yeah. F limit is 0. Yeah. So it's gone. Yeah. And 0, you have this part. Yeah. So then, that one. Yeah. So the other one, yeah. So integration by parts, yeah. Limit at infinity, 0. Yeah. So 0. Yeah. So there you have that. Yeah. All right. So very easy to see the property. Yeah. All right. Yeah. But the next we will look at the definition of the Fourier transform. So that one is the most commonly used one. Yeah. So these two, the usage of these two transforms, not as much as the Fourier transform, containing both cosine part and the sine part. Yeah. But there is one big difference. For Fourier cosine transform and Fourier sine transform, when our f function is a real function, real value, the function value is real number. After transform, we also get a real function, right? Yeah. So from real function to real function. Yeah. Very natural for both of these transforms, sine, cosine. But for Fourier transform. Yeah. Fourier transform, because we need to use the kernel e to the ix, there is an I inside. That means when we apply it on a real function, we get a complex function. Because the complex part not gone. See, so your Fourier transform, it returns a complex function. The real part and the imaginary part. Two parts. Yeah? So that's the main difference. Yeah. 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 Then, when you come back, you get a real function. Yeah. But the thing is, all right, we know our computation has a lot of errors. A lot of errors. So when you do the Fourier transform, you get a complex function containing small errors. All right? Due to the error, when you apply inverse Fourier transform, so you may not get a completely real function, right? Yeah. Because the error may cause some precision problem. Yeah. All right. Yeah. Let's stop right here. Yeah. So, yeah. So, yeah. Next week. Yeah. Yeah. The homework assignment. Yeah. So you need to work on the homework assignment number 3. The deadline is next Friday, right? Yeah. I said next Friday, the deadline, but I plan to give you a 1 day grace period. Yeah. So 1 day grace period, and I need to assign last homework assignment next week. Yeah. After homework assignment number 3 due, then I need to assign our final homework assignment, last one, next weekend. Yeah. All right. All right, that's it.